Welcome to EDU World Space.
Okay, this question has a lot of parts, but we'll be able to get through it. The question begins by telling us that the detailed calculation of the Z effective of the outermost electrons in sodium and potassium are, I'm going to write these to the side here so we have them for reference. For sodium, it's positive 2.51, and for potassium, it's positive 3.49. And then it asks, what value do you estimate for Z effective experienced by the outermost electron in sodium and potassium, assuming the core electrons contribute 1 and valence electrons contribute 0 to the screening constant? So part A, it tells us core electrons, S equals positive 1. And now it wants to calculate the Z effective for sodium and potassium with this new calculation. So Z is just the number of protons, and for sodium that's 11, potassium it's 19. And the number of core electrons for sodium is 10. So I'm going to write minus 10 times 1, because it tells us that's what S is for the core electrons. It gives us a value of plus 1. And for potassium, that number is 18 core electrons. Again, they contribute 1 to the screening constant in this part of the problem, so that also gives us plus 1. In B, it tells us to use Slater rules to do the same approximation. The Slater rules say that electrons in the shell n-1 contribute 0.85, and electrons in the shell n-2 contribute 1. So again, these are both 11 and 19. The nuclear charge does not change, but we'll be subtracting their numbers now. So in sodium, there are 8 electrons in the n-1 shell. So this would be 8 times 0.85 plus there are 2 electrons in the n-2 shell. So 8 electrons in the n-1 and 2 electrons in the n-2. So this gives us positive 2.2. And for potassium, there are again 8 electrons in the n-1, so it's 8 times 0.85 plus there are now 10 electrons in n-2. Really, there are 8 in n-2 and 2 in n-3, but they can't contribute more than 1 to the screening constant with these equations. So we're just going to call them all n-2, so 10 times 1. And this also gives us an answer of 2.2. Great. And then it says in part C, which approach gives you more accurate estimate of Z effective? And for between these two, between plus 1 and plus 2.2, clearly using Slater's rules gets us closer to these. So it would be, I'm going to write method B. And in part D, it says, does either method of approximation account for the gradual increase in Z effective that occurs upon moving down a group? So from these real numbers, you can see that we move down from sodium to potassium, we increase our Z effective by about 1. But in both of these approximations, you can see that the Z effective is the same, regardless of where we are on the periodic table, which row we are. So no, neither approximation accounts for the change in Z effective as we move down each group. Then in part E, it asks us to predict the effective nuclear charge of the outermost electrons in the rubidium atom based on the calculations for sodium and potassium. So here you can tell that the difference between these two is about 1. So we can estimate that if we go down one more group to rubidium, which is just below potassium, we would go up by, again, about 1. So I would estimate that this is, I'm going to do the squiggy to say it's about 4.5. So based on the calculations here, if we go down one more row, we can expect effective nuclear charge to go up by about 1 or about 4.5.